Section 4, we're going to look at determinants of square matrices. Now, we've already talked about the 2x2 matrix. That one's fairly simple. One thing, though, the notation, you can also use absolute value bars. One thing to not get confused by, you'll see it written both ways, determinant of matrix A or the absolute value of matrix A. It does not mean flip everything to positive. It doesn't actually mean perform absolute value. It means perform finding the determinant. Okay? So it'll give you a single number that kind of summarizes something about it that you use for other things. So the 2x2 is the same process as what we have done already. So what would be the determinant of the first matrix here? 7. You just literally follow that pattern. Take 10 minus negative 3. Okay? And I always just use that pattern for it. Oh, 13. What did you say, 7? Anyway. Hopefully I would actually look at the problem. What about the next one? Last one? 0. It's 6 minus 6, 0. Okay? Now, the problem with larger matrices is you need to actually look for something a little bit different with them. Okay? You need to break them down into smaller pieces. To do this, we're first going to look at finding what are called minors and cofactors. Okay? Now, the minor of a matrix, there's not just one. There's one for every single entry. So when this talks about finding what's called the minor, it's one for each position, ij. And to do it, you take whatever that number is in the original position, you ignore the row and column that it's in, and you take the remainder of it and find the determinant of what's left. So if you cut out the row and column of a 3x3 matrix, you're left with just a 2x2. Okay? And you just find your determinant. Now for cofactors. Cofactors, you're going to do this process. -1 raised to the I plus j. Now remember, I and j are your positions, right? So row 2, column 3, that kind of thing. Okay? That number, well, if you take -1 raised to an even number, what do you get? +1. If you take -1 raised to an odd number, you get -1. So all this is saying is it's positive or negative based on whether that I plus j is odd or I plus j is even. Well, if I add two numbers together and they're even, what's got to be true about the two numbers? If you're going to add any two numbers together and guaranteed to get an even number, what has to be true about those two numbers you're adding together? They both have to be even or they both have to be odd. If they're different, when you add them up, you're going to get an odd number. If one's even, one's odd, you're going to get odd. If they're both even or both odd, you're going to get even. Okay? Position-wise for a 3x3, the really nice thing is what ends up happening, because this primary diagonal is literally the numbers 1, 1, 2, 2, 3, 3. Well, these will always be positives, right? Anything that's just one off of that, so if I look at the positive here, this next one would have to be negative because it's one number bigger. This one down here would have to be negative because it's one number bigger. You just kind of get this alternating pattern of pluses and minuses. Now, it's not saying that that number is actually positive or negative. It's saying whether you flip the sign or not. Okay? If you have a plus here, you leave the sign with whatever it is. If you have a minus, you flip the sign. Okay? That's a little bit confusing at first, so let's actually look at one broken down. For this problem, for the minor of 1, 1, well, I'm going to look at the 1, 1 position. I'm going to ignore everything in that row, everything in that column. And for the minor, I'm going to find the determinant of what's left. Well, what would the determinant, and that's why these are in absolute value bars, that means find the determinant. So what is the determinant of that matrix? Negative 1. So that's your determinant. Now, by its position, the cofactor of 1, 1, well, would that change signs? Remember, if it's even when they add them up, it doesn't change signs. So 1 plus 1 is? 2. So it's even, doesn't change signs. Stays -1. Don't make that harder than it is. So if it's asking for minors, it's asking for this number. If it's asking for factor, I almost said cofunction. Cofactor, it's looking for this number. Okay? So let's do this for an entire matrix. How many minors will I have?
2.
There's 1 for every single position.
Oh,
So you'll have 9. Cofactors, you'll also have 9.
Ice cold.
Okay, so if I want A11, if I want to find M11, I'm going to look at this 3. I'm going to ignore this row. I should turn this on. I'm going to ignore this row and this column. So I want to find the determinant of what's left. Well, what would be the determinant of that? 9. 12 minus 3. So this would be 9. Minor of 1, 2. Again, I'm going to ignore the top row, but now I'm going to ignore this middle column. I'm just going to look at the left and the right. What would you get there? 19. You have 18 minus negative 1, so 19. Is that making sense? M13, I'm going to cover up row and column. Yeah, 9 minus negative 2 would be 11 minus negative 2. Okay? And you just keep going. What would 2, 1 be? Oops. Yeah. 2, 1, I'm going to cover up this column as well as the middle row. So negative 12 minus 12, negative 24. Okay, so I'm ignoring this and I'm ignoring these two. Okay, cover up the middle row and middle column. So 3, 6, negative 1, 4 gives you what? 22. 2, 3. 11.
3 minus 12.
So 2, 3. Cover up this. So I get 9 minus 2. Yes. 7. 3, 1. So there.
Oh.
Negative 10. Negative 2 minus 8. 3, 2. So middle column and these two. Yep, negative 9, 3 minus 12.
Yeah, for 3, 1, it was negative 10.
Why did I write 2? Anyway, I think I might have said 2 when I was doing the problem and I wrote it down. 3, 3.
12.
Yep, again, 6 minus negative 6, 12. Now for cofactors, anything where they're both odd or they're both even, I'm going to leave the same. The ones I'm going to switch are the ones where the two numbers are different. So, going down this list, which ones am I going to switch the sign on? Well, the one where there's one even, one odd, right? So 1, 2, 2, 3, and 3, 2. So everything else is going to stay the same. This is still 9. This one flips to negative 19. Cofactor for C13 stays 11, and then you just kind of go down the list, flipping only every other one.
Can you explain that again? Why they're odd?
It's if you add their position numbers. So this is row 1, column 2. So you literally add 1 and 2.
Oh, I see.
So it's odd.
Right.
Okay, it's what causes it to be an alternating format. You can honestly also just use the fact that prime diagonal, and this works for larger matrices as well. If you make that main diagonal be all positives and then just alternate out as you go, positive, negative, positive, negative, positive, negative, positive, negative, positive, and it needs to always be alternating as you go,
So like on a
horizontal or
on
vertical.
every 3, 3 matrix, there's the same ones. Are always gonna be
Yep,
odd.
those 4 will always be will always flip signs. Everything else will remain the same on the sign. Okay, and if you up it to a 4, 4, it would just flip to this. Okay.
Yep.
So 24 flips, 22 remains the same, 7 flips, negative 10, positive 9, and positive 12. So those would be your minors and your cofactors. Since it's asking for that, those would be your answers. Okay? Yeah.
What does a minor and a cofactor tell me?
It's actually kind of like a one-step, be able to find the determinant. Okay? So if I want to find the determinant of one of these 3 by 3 matrices, if I could talk, I need to use those cofactors. Okay, use the minors to get to the cofactors. So what this is saying, determinant of a square matrix. If you have, honestly, 2 by 2 or greater, but we're not going to bother if it's smaller than a 3 by 3. So what you want to do, the determinant of the matrix is the sum of the entries in any row or column, so your choice, multiplied by their respective cofactors. So what that means, I can take any row or any column. I don't need to do the whole thing. I just need to do one of the rows or one of the columns. Doesn't matter. And then I want to take the one in the actual position times the cofactor of that, plus the one in the next position in that row times the cofactor, plus the one in the next one times that row, however big it goes. You just do one row or one column. Yep. So if I look at a problem like this, and actually that'll be called expanding by cofactors. And honestly, for this is where you find the determinant by expanding by cofactors. On the test, you'll have a problem that flat out says this. This is one of our standards that we got to hit for the state, that you need to be able to solve these using cofactors, find the determinant. Okay? So you can verify your answer with the calculator, because this won't be on the quiz. You'll have a calculator. But you need to show the full process. Does that make sense? Okay. So let's look at one. Now, it's actually completely your choice which row or which column you do. Okay? I actually probably wouldn't do 1.
Second row.
Why?
0.
This is 0. That 0 is going to make things easier. So if I look at this row, I'm going to find, if I want to find the determinant of A, I'm going to take the values coming from the second row. So A21 times C21 plus A22 times C22 plus A23 times C23. Okay? So essentially just fill these in. A21 is what? 3. Now for C21, I'm going to take it times. Now one thing to watch out for this. Remember, you have that pattern of positive, negative, positive, negative, positive, negative, right? So I'm going to actually put this in parentheses. I'm going to put negative the determinant. So what matrix would I plug in there? If I cover up the first column and second row.
4 and -2.
Okay? That kind of makes it a little bit clearer what you're doing. So then I'm going to add to that A22, which is what?
5.
Now, is C22 going to flip signs?
No.
No. So I just need to take it times that determinant. And what numbers are going to go into C22? 3, negative 2, negative 1, 1. Again, plus A23 is 0, right? So do I even care about this? No. It's going to be 0 no matter what it is. So, what's your determinant for the first one here? 4 minus negative 8 will be 12, and it flips to a negative because of what's out front. Right? What about the next one? 0. 3 minus 2? 1. So, I get what two numbers? Which add up to be? Negative 31. Okay? So that's using cofactors. Now, there is another method. Okay? For any time you actually need to do this, I usually don't bother with this method. I never remember it. I have to look it up every year. Okay? The way I learned it, I didn't actually know the name of it, but it's kind of an extended version of that loop that we do for smaller ones. Okay? The loop we do for smaller ones is actually a method called basket weaving. Okay? You can do it with larger matrices, but you got to modify them first. The problem is I need to use diagonals here, but I need to be able to hit every single number with diagonals. To do that, I need to make this matrix larger. So what I'm going to do is I'm going to duplicate these first two rows. Okay? If it's solved by cofactors, you need to do this, you get your answer. If it doesn't, I honestly usually go with this method if I don't have a calculator, where I duplicate these two rows at the end. So I'm going to take 3, 3, negative 1, 4, 5, 4, negative 2, 0, 1, and then I'm going to recopy 3, 3, negative 1, and 4, 5, 4. Okay? Then I'm going to use the same process as what we do on the other one. I'm going to take the diagonals, but I don't have just one diagonal here. I have 3 going downhill here. So here, here, and here. Well, if I multiply on that diagonal, what do I end up getting for the first diagonal? 15. What do I get for the next one? 0. Next? Negative 24. And then I'm going to add those 3 numbers together. Now that's not enough though, because I also need to do the diagonals going uphill. So I'm going to go this way, just like we do, you're kind of going down and around when you're doing a 2 by 2, right? And then you subtract. I'm going to do the same thing here. I'm going to go up this diagonal, giving me what? 10. Go up this one, and go up this one. 12, yep. So then I'm going to add those together. If I add those together, up here I'm going to get 22. Down here I get,
Is that 15 or 20?
that's 15 there. Negative 9. Okay? Then, just like here, the down diagonal minus the upward diagonal. So in other words, negative 9 minus 22 equals negative 31. I like this method because it just follows that same pattern. The cofactor method works as well. The test will require you to show the cofactor method, okay? Questions on those? One more. Find the determinant of this matrix. Okay. Well, let's look at cofactors. Which row or column would you like to do?
Third.
I would do column 3. Because you're going to eliminate 2 of your values. Right? So when I do that, if I want the determinant of matrix A, I'm going to take which position?
Negative 4.
Yeah, row 1, column 3.
Oh.
It'll be negative 4, but the A, 1, 3, times the cofactor of the same thing, plus 2, 3, times cofactor of 2, 3. Now from there, honestly, what's A, 3, 3? 0 times whatever, plus 0 times whatever. So all I really need to do here is find negative 4 times, now here's where it gets a little bit ugly, because if I eliminate this row and the top, or this column in the top row, there's the matrix that goes inside there. So you have 2, negative 2, 6, 1, 5, 1, 3, 1, negative 5. Then you're going to add to that. Now the other thing, is this going to be positive or negative in this position, the cofactor? Is it going to flip signs or stay the same? Stay the same. What about this one? Flip. So I have plus 3 times negative, and then your determinant. Well, if I eliminate this row and the circled column, okay, so I have 2, 6, 2, 1, 5, 1, 3, 1, negative 5. So now how would I go about finding the determinants of those 3 by 3s?
Use the calculator.
Yeah, honestly, 4 by 4 I'm never going to ask you to do by hand. So go ahead and use the calculator and find your answer.
Thank you.
God bless.
Not that mean, am
A little sometimes.
Maybe.
I think you could have us do it like once on our own.
I? But not on a test.
No, you make it extra credit. Multiply it.
That does seem like
Whoa.
Extra
Without the
credit?
calculator.
Me? Never.
Well, I'm fine.
Go ahead and punch the 4 by 4 into the calculator. Where's the determinant at on your calculator? You go to matrix. The middle thing is math. The very first thing on there is DET.
Hey, it was meant to be.
So put in your 4 by 4 matrix, quit out of it, and then go back into the matrix menu, go to the middle, math, put in the DET entry, Then go back and select your 4x4 matrix. Anybody else get 704? 704. Honestly, a 4x4 one wouldn't be on the test anyway. But it is good to practice some of those more challenging ones. Just because if you can do those right, you're probably pretty good on the easy ones. Questions on any of it? Okay. The rest of the time is yours. Make use of it.